Welcome to EDU World Space.
So in this problem, we're asked about doing a Taylor series expansion. So we have a cable that's sagged between two supports that are at the same height. We have this function that describes the
Here's a clean and professionally formatted presentation of the calculation shown in the image.
And so what I'm going to do is I'm going to actually, they don't really
Application
ask you to
of
do
the
this
work
in the
energy
book,
theorem,
but you really
wet.
kind of
From the
should
work
think about
energy
it more this
theorem,
way.
the force F is
I'm
given
going to
by
define
F equals
this
the
to
frac
be
text
x hat.
KE, where
And if you
KE
notice,
equals
that is
kinetic
a
energy,
the x hat
S equals
is
stopping
has
distance.
no
Then given for object A,
It's a
FA equals
dimensionless
frac
variable
100,000,
because
0.10.
W naught
For
over
object
FH
B,
has the
FB equals frac
dimensions of length.
225, 1500
And
equals
that had better be the
0.15
case
text
because
space
we
in.
really
And
can't be
force
taking
ratio
the
frac
hyperbolic
FA, FB
cosine of
equals
something
frac
that has
0.10,
dimensions in it.
0.15 equal frac 2 null result.
And then I'm going to
Gamma
divide
box frac
both
FA,
sides by
FB.
this value,
Would you like a
which also
PDF
has
version of this
dimensions of
explanation?
length. So this has dimensions of 1 over length, I should say, so that this has dimensionless. This has dimensions of length. So I'm going to define y hat as W naught over FH times y, and then x hat. So y hat of x hat is just the hyperbolic cosine of x hat minus 1. So if we non-dimensionalize this equation, we just get it. We basically, both of our parameters go away. And now what we're going to do is say, okay, let's say x hat is small. Well, if x hat is small, we can take a Taylor series. Now, if we plug in x hat is 0, we get 0. We take a derivative of this with respect to x hat and plug in 0. So then this goes away. This becomes hyperbolic sine, and hyperbolic sine of 0 is 0. And so that's our first derivative at 0 is 0. And then we take two derivatives. This goes away. This becomes hyperbolic cosine again. Again, with hyperbolics, the sign doesn't switch like it does with the regular trigonometric functions. So the second derivative evaluated at 0 is 1, which means our Taylor series, this is our first non-trivial term in our Taylor series. So our Taylor series for y hat as a function of x hat is 1/2 x hat squared. So at that order, we can obviously take more terms. The next term would actually be 0 because we're going to get another hyperbolic sine, and then the next term we'd have an x hat to the 4th. And again, we could take this out, but they just said to take it to only the first two terms are retained. Let's see here. I guess basically I think they meant these two terms. But anyway, we could, if we wanted to, let's see, this would be then 4 factorial, let's see here, 4 factorial 1 over 12, 1 over 24 x hat to the 4th, I think we get out here. But anyway, this what I think they're getting at is that this looks a lot like if we had just assumed that the weight was uniformly distributed along the horizontal axis and not along the curve. So if we did that, we would just get the simple equation of a parabolic cable shape. And so if we plug all this stuff back in, you see that y of x is approximately W naught over FH times x squared. And this is again what we would get if we had just assumed that the weight was distributed horizontally and not along the curve. So when we have, you can think of this as more, if we have a very sag curve like this, a lot of the weight is actually over here, right? And a lot of the weight is over here. It's not uniformly distributed over the horizontal distance. So what this says is that this is true. This is a good approximation if this thing, x hat, is much less than 1, which says that the maximum x is going to be half of the span length, So that would be, we could put in like L over 2 here, or let's call it D over 2. And so then we would need this and this to be very large or this to be very small. And what that means is that we either have a very light cable, which won't sag too much, or we have a lot of horizontal force, which would also reduce the sag, right? So the more you pull on this, the tighter you pull the cable, the less it's going to sag. You can just play around with that with a piece of string. So that's what we get so this is a good approximation for a very small sag.